All right, let's share my screen. Where are my slides? Here. All right. All right. Good afternoon, good morning, good evening, everyone. Welcome once more to J4K. My name is Igor. I'm a software developer here at IBM Canada, and I'm very excited to share with you what I've been working on and garbage collection. So let's get started. By the way, this section is recorded, so I'm probably in the chat right now. So if you have any questions, I'm more than happy to take any as you watch through the session. So these are just some disclaimers saying this is presentation just for information purposes only. So don't blame us if something blows up. All right. I'm going to talk today mainly on garbage collection. So this is basically what I'm here for. Hopefully you're here for that too. And that's going to be the bulk of the talk. And the last 10, 15 minutes, I'm going to be talking on some advanced concept that what we call double mapping arraylets, which is just one way for us to optimize large array allocations in the heap. So if you want to try out some of the stuff that I'm going to be talking to you about today, I highly recommend downloading the binaries of OpenG9 to adopt OpenGDK, and I also recommend comparing OpenG9 with hotspots, which are, I think, the two main JVMs out there. So OpenG9 came to the open very recently. For those who doesn't know, it's IBM's JVM. It's been on the works for more than 20 years, but has only came to the open in 2017. Before it was called G9, now it's OpenG9. It's under the Apache 2.0 license and Eclipse public license. And a fun fact here is that OpenG9 started as an embedded JVM. If you might remember Java ME, Java Micro Edition, and started as it would fit into the, I don't know if you remember, the Nokia 9300, very old phones. So because of that, OpenG9 has a very low footprint, and I recommend if you're concerned about memory usage to try out OpenG9. So garbage collection. So what is garbage collection? So here is a by the book definition. Garbage collection is a form of automatic memory management. The garbage collector attempts to reclaim memory occupied by objects that are no longer in use by the application. And that's in contrast with languages like C, C++, where they don't have an automatic memory reclamation system, where in order to allocate and deallocate memory at the heap, you need to manually call APIs like malloc, new, delete, and free. So with that, garbage collection has a few responsibilities. It allocates memory, it identifies liveness of data, and reclaim garbage. So all that data or objects that are not considered live are considered garbage, therefore it's going to be reclaimed by the garbage collector. So there are some positives for GC. It's an automatic memory management, and it helps reduce some categories of bugs, for instance, dangling pointers and double freeze. And frees the programmer of the burden to manually allocate and deallocate memory. On the other hand, we also have, we have negatives, which GC requires additional resources, CPU, memory usage, causes unpredictable pauses, and that's what we call stop-the-world pauses, may introduce runtime costs. Application has little control of when memory is reclaimed. So it's a trade-off, right? But it does have this positive and negative. So, and like I said, you're gonna have pauses, and depending on the policy you choose, the pause is going to be longer, it's going to be less, it might hurt the throughput of the application. So hopefully by the end of this presentation, you're going to know how to tune and choose which policy is better for your own application. So there are quite a few GC algorithms out there: reference counting, mark sweep, region-based, generational, mark sweep, compact, parallel, concurrent. I wish I could go through all of them, however, I don't have the time to do that. At the end, I'm going to reference you through a book where if you're curious, you can search for them. And I'll be talking to you through different GC policies. I'm going to mention some of these as like live experiences. So these are the policies or configurations of the GC that I'm going to be walking you through today. So the first one of throughput, it's a stop-the-roll parallel collector. GenCon is a generational copying collector. GenCon CS is a pauseless collector. Metronome incremental software real-time collector. Lastly, the balance, which is a region-based collector. If you're familiar with hotspot GC policies, GenCons is very close related to CMS. GenCon CS is a pauseless collector. You can think about Shenandoah, they're not very similar to each other, but both pauseless and balance is very closely related to G1. So our first policy, opt throughput. Opt throughput is a parallel global collector, meaning multiple GC threads are running in parallel trying to collect the heap, but all the application threads are stopped, which means the GC works in a stop-the-roll manner here. The GC cycle is divided into three phases: mark, sweep, and optional compaction. I'm going to go through them in a few minutes. And all GC operations are completed in parallel, like I just told you. And there's also a little bit of overhead of the mark map and work packets, which is just some metadata required by the GC to help reclaim the objects. So every time you start your application, the GC is going to instantiate a heap, which is the memory regions where all the objects are allocated. Normally, this heap is a contiguous region of memory. It doesn't have to be, but I would say 90% of the time is a contiguous region of memory. And in the case of opt-throughput, this region of memory is further divided into two logical memory areas: the small object area and the large object area. Most objects are located in the small object area, while if objects are larger than 16 kilobytes, they are stored in the large object area. Now, this is how an application behaves under this policy. So the white arrows here is going to be represented as the application threads, and the red arrows are the GC threads. So the application starts allocating data, and once it exhausts the heap, then the GC is triggered. So all the application threads are stopped. GC starts its operation, collects objects, and then when that's done, application can continue from there. And these GC operations here are stop the world, where the applications, you might experience some delays. So like I mentioned before, the opt throughput is divided into three phases: marking, where GC goes through the object graph and marks all live objects; sweeping, where GC reclaims memory for that object, meaning all those objects that were not marked in the marking phase gets reclaimed here. And we might compact the heap if we think it's necessary. So what is a fragmented heap here? So imagine your application starts, there's many allocations, some GC cycles, allocation, GC cycles, and eventually the heap can get fragmented, meaning you can put all these little free spaces together, and combined, you might have enough space to allocate an object. However, you don't have a contiguous region big enough to allocate that object. In that case, we would need to compact the heap, where you take all the live objects and put into an area of the heap, resulting in this new huge free space where we can start allocating objects again. Next, that's output. Now we're gonna go to the next policy, which is GenCon. GenCon is a generational copy collector. Here, objects have ages. And this is a very good collector because it works under the weak generation hypothesis, meaning that young objects tend to die young. Objects newly allocated tend to die very young. So it provides a significant reduction of GC stop-the-roll pause times, introduce a write barrier for the remember set list, actually introduce 2 write barriers, and I will explain you why and why do we need them. And in this case here, we have a concurrent marking phase. Before, the marking phase was not done concurrently with the application. Here we have a global concurrent phase. Here, the heap, instead of being divided into small object area and large object area, divide them into nursery and tenure. Nursery being the new space, tenure being the old space. And the nursery is further divided into 2 logical areas, allocate and survivor, where all objects are actually allocated in the allocate space. And once that's consumed by the application, the GC triggers what we call scavenger, which is a copy collector, which copies all live objects from allocate to the survivor space. And when that's done, we flip those spaces and start allocation again. So this is how an application behaves under the GenCon policy. Again, the white arrows represent the application threads and the red arrows represent the GC threads. So like I said before, scavenger is a copy collector, copying objects from allocate to the survivor space here. And this is a stop the world copy collector. So once that's finished, then application can continue from there. Then we might have some other scavenger. And you might ask yourself, so when do we actually collect tenure objects? That's where the global marking phase comes in. That's where we are concurrently marking the tenure objects. And that actually run concurrently with the application. That's where the yellow arrows come in. Those are GC threads running concurrently with the application. We might have scavenger overlapping with that. And at the end of the global marking phase, we sweep the tenure, meaning we collect all those tenure objects that are not reachable. And now write barriers. So you saw here that we have a concurrent marking phase here. And that can be a problem because of we are concurrently marking objects, but at the same time, we are also allocating objects. So to prevent some racing conditions and some bugs, we have what we call write barriers. So write barriers are piece of codes that the JIT introduces whenever we have a store in order to solve some issues. For instance, let's consider the following case. We have the following object graph. GC is in the middle of collecting the heap. GC already traversed all the roots, all the root objects, already traversed object A, is in the middle of processing object B, and still haven't seen the object C yet. Thread comes along and changes reference from B to C to A to C. And then GC is in the middle of traversing object B and is going to say, okay, B doesn't point to anything, then I'm done with that. Then that's the resulting object graph. However, GC is also done. And then it's going to collect C erroneously because it missed its reference from A to C because it has already seen A and another thread input that reference there. So we need the right barriers to prevent scenarios like this. So imagine we have a store there, we are storing object C into a field of A, and in there we check if a concurrent GC is active, we dirty the object A. in that case, at the end of the GC, we go through all the dirty cards, and that way we would prevent snares like the one I just mentioned, and we would actually remember A. That's not the only right bearer that we need. We do need another bearer because there might be some objects from old space tenure that might point to the new space. And whenever the copy scavenger are running, it might miss these pointers from the old space to the new space. So we need a right bearer to make sure scavenger remember those. So here is the same store. And in order to check that, we check if A is tenure, meaning if A is in the old space and C is in the new space, we remember that object. And since we have two barriers here, we can include that in the same check here to save some time. So that's the right barrier for GenCon. Now our third policy here is GenCon CS. CS stands for concurrent scavenger. Is an improvement on GenCon, where the biggest difference here is that scavenger, instead of being stop the world, here is going to run concurrently with the application. Introduces a new barrier, here a read barrier, because here we are moving objects with the application thread. Concurrently with the application thread, sorry, it is considered a puzzle GC. So the heap layout is the same as GenCon. We have allocate, survivor, and tenure space. And here is the biggest difference. So again, the white arrows represent the application thread, and the red arrows represent the GC thread. To remember, before CS was only one stop the world cycle, here is concurrent with the application. So we're going to actually have two concurrent, two stop the world pauses, one at the beginning, one at the end of the concurrent scavenger phase, where the one at the start, it marks all the root objects, and then it releases the application threads, and this cycle runs along with the application. And then at the end, we have also a very short stop the world pause to bring all the threads into synchronization and let the application run from there. And then there we might have another scavenger, concurrent scavenger, and we have all those steps again. And global start here, the global marking phase is still the same. Nothing has changed there. All right, so you might imagine here we are moving objects as objects are being allocated, and there might be some race conditions. And in order to prevent some problems there, we have what we call read barriers. And if you're familiar with Shenandoah version 2, they have a very, basically the same barrier as we're having here. Shenandoah version 1 has Brooks pointer, and version 2 they updated that to use a similar barrier that we're using here. So what we do is, imagine we have two threads, one GC thread, one application thread, which is the mutated thread here, and they are trying to access the object. GC threads trying to copy that object to space, and mutated threads trying to access that object. In order to prevent the risk here, we unconditionally copy both objects to the to space, and we do a CAS, an atomic operation, to insert a forwarding port in the header of the objects, and whoever wins that, that's going to be the copy of the object that we're going to be using throughout the application. And whoever loses that, the race is going to discard its copy and use the one that actually won. So this is how it happens. So both threads try to access the object, both copy the object unconditionally, and they try to race to install the forwarding pointer. So here in this case, GC thread 1, the race, mutated thread is going to be, okay, I lost the race, therefore I'm going to discard my copy, follow that pointer and access the actual copy that we're going to be seeing throughout the application. Therefore, we have a consistent view of the object and we don't have any dangly garbage, or we're not accessing garbage in the heap. So that's concurrent scavenger. Now, Metronome. Metronome is a bit different. It's an incremental software real-time collector. It provides an upper bound on GC pulse times, meaning, imagine you have a 10 milliseconds window. Metronome guarantees that 7 milliseconds out of those 10 milliseconds, meaning 70% of that window, is going to be dedicated to the application, while the other 30% is dedicated to the GC to do whatever it wants to do with those 30%. It can do GC work, or it can give some of that time back to the application, which is why it has a upper bound on GC pulse time. Here we use a different barrier. We concurrently map object as well, but we use a snapshot at the beginning barrier. I'll explain later the difference between the barriers that we've seen already. And it has a high percentage of floating garbage because of this SATB barrier. Now the heap layout is a bit different from before. Here we divide the heap into regions, fixed size regions, more specifically 64 kilobyte regions. And the bigger the heap, the more regions we're gonna have in this policy. Allocations is based on cell-based allocation, meaning in a specific region, you're gonna find objects that are of the same size. And cell size range from 16 to 2 kilobytes. And there comes some positives of having objects of the same size in a given region, because if you have chunks of spaces in a specific cell size and you want to allocate object of that specific cell size, you can just allocate right there, and it's quite fast. And that's opposed to, as you're going to see in the future, balance, which uses generational aspect to it. Okay, but back to Metronome. Objects larger than 2 kilobytes are still consumed as in contiguous regions. They can overlap regions, with the exception of arrays. If we have an array that's larger than a region, meaning larger than 64 kilobytes, we actually divide that array into chunks. So, for example, imagine we have a 128 kilobytes array. We're going to divide that array into 2 chunks, put that into 2 separate regions, and in the header, we're going to have pointers to point to those chunks, which is just a clever way of storing large objects in a heap. So this is how the application behaves under the Metronome policy. Again, white arrows represent the application threads, and red arrows represent the GC thread. So this is a very simple GC policy. So remember, up throughput from our first policy, where we have that big pause time, the big stop the row pause time. So take that stop the row pause time and divide into increments, into chunks. That's what Metronome is doing. It's taking that big stop the row pause time, and through some heuristics is going to collect the heap into cycles, into pauses, where it's not going to surpass that 30% gap into a specific window, and it's going to collect the object into chunks. So it's going to collect the heap a little bit here, then a little bit here, then a little bit here, which is why it's called an increment collector. So Metronome uses what we call snapshot at the beginning barrier, and differently from the other barriers, it can cause a lot of floating garbage, and the barrier has to be done before the store. So now let's imagine the following object graph here, and the following scenario. GC is in the middle of traversing the object graph. It has already visited the roots, is in the middle of visiting B, it has already visited A, and has not visited neither object C and object D. a thread comes along, adds a reference from A to B, and another thread, or the same thread, deletes the reference from B to C. And that's exactly the point where the barrier is triggered. So if we didn't have the barrier, this is what the resulting object graph would be, where we would erroneously collect object D. But with the barrier, we're gonna keep that reference and we're gonna remember object D. But as a consequence here, we also going to remember C. Even though that's a garbage, we are going to remember C because we're keeping that reference, because D is reachable from B, but C is right in the middle of it, so there's no helping there, and we're going to have to remember C, and that's what we consider floating garbage. This is how the barrier here is implemented. So imagine you have a store and actually put the code of the barrier before the store. So we temporarily take that field that is going to be soon to be deleted, and we check if the barrier is active. We remember that, that reference. And at the end of the GC, we go through those remembered references and traverse those as well to remember those objects. So that's Metronome. Last but not least is Balance GC. If you're familiar with the G1 policy from Hotspot, this is a very close sibling to it. Both are region-based, both are generational. One difference that I can think of is that G1 only keeps 3 different ages, and we keep, I think it's 21, 24, and you're probably gonna swap that in the future, I think, to 7 regions, but they are very similar policies. So Balance is a region-based generational collector, where regions here is going to have ages. It provides significant reduction on max DC stop the row pause times, introduce a right barrier because we can have inter-region references, and it has an incremental heap defragmentation, which is, I actually have a very cool graph that I'm going to show you in a little bit. So very similar to Metronome here, the heap is divided into regions. However, we try to keep between 1,000 to 1,000 regions. Therefore, the bigger the heap, the bigger the region is going to be. We allocate regions in regions that we call Adam regions, and we try to locate in a region that's close to a NUMA node. So this policy is very good if your system supports NUMA nodes. If an object is larger than a region, we're going to throw an out-of-memory error with exceptions of arrays, where you're going to have the same technology in Metronome, arraylets, where if this array surpasses a region size, we're going to divide that array into chunks, put that in different regions, and the header is going to point to those regions, and we call those arraylets. At the end, I'm going to spend 5 to 10 minutes explaining arraylets in more detail, so don't worry about that. So this is how application behaves under the balanced GC policy. So here, PGC stands for partial garbage collection. It's a copy collector similar to the one from GenCon, the scavenger, remember? So PGC use some heuristics to try to select those regions with the greater return of investment, meaning those regions that is going to have the most garbage, and collect those regions. And it's going to take the live objects and copy from one region to the other. When that's done, we increment the age of those objects. And in one specific region in balance is going to have an age. So all objects in that region is going to have a specific age, not the same size as in Metronome. Now, the problem here is that PGC only have local knowledge of these regions. And as the application goes, it loses this local knowledge. So GMP is there to help PGC. GMP stands for Global Marking Phase, and all it's doing is marking objects in order to help update PGC on this local information. And GMP can overlap with other PGCs, with all other copy collectors, which is the PGC. And that's how the application behaves in this case. So what is GMP actually doing exactly? So like I said, it's not reclaiming any memory. It performs a marking phase only. It is scheduled to run in between partial GCs, in between these copy collectors. And PGCs is a stop the road here. Global marking phases is marking objects concurrently. It builds an accurate mark map of the entire heap, and this mark map is going to be used by the PGC when it's done, which is why it updates its information. It describes the remember set call list at the end. So look at this graph here. In the x-axis we have time, and then y-axis we have free heap. So the higher we go, the more free heap we have. So the lines going up is the PGC collecting objects. The lines going down is the application allocating objects and exhausting the heap. So you can see there's actually a trend going down where as the application goes, as we collect garbage with PGCs, you see that with time, as application allocates objects, we reach more and more and more the end, the heap limit, right? So if that trend continues, we would probably hit out of memory error. So GMP knows, okay, I need to kick off here so that by the end of my cycle, I can update PGC's information so that it can defragment the heap. So that's what GMP is doing here around time 70 until 150, 160. It's doing a global marking phase, and when it's done, it updates the partial GC data information, and then that's where you see this red line there, and which just starts to fragment the heap slowly, which is where you see this increasing in this increasing pattern where the heaps gets defragmented by the PGC. Then once again, that trend comes down again, then we kick another GMP and the application continues from there. And so in balance, we do need a barrier. Remember, we might have references coming from different regions coming to this region, and we need a way to remember those references. Remember, in GenCon, we have references going from old space to new space. It's kind of similar here, but we have multiple of these regions. So in order to free the burden of the mutator, we have an unconditional barrier there where we dirty the card, and at the beginning of PGC, we go through all those cards and check if there's an inter-region reference. If there is, we add that to the remember set card list, and then at the end of the PGC, we go to that remember set card list to remember those objects. It's always a trade-off. So you have to think about whenever we implement the right barriers, do we want to burden more the mutated thread, which is the application thread, or the GC thread? So it's always a trade-off. So that was a little bit on GCs. Now I'm going to explain a little bit more in depth what array-lets are. So array-lets are used in the region-based collectors, Metronome and balanced, and that it's a clever way to store arrays, large arrays in a region-based collector. An array-let spans are located like a normal object, and each leaf considers an entire region. So here's a visual representation of what I'm talking about here. So that's the heap. And in the bottom there, we have the header of the array. So the green there, we have array-let spine. We have the header, like the class, the size, and arrayoids are the references to the array data. So we have three references here that point to three regions in the heap, and the leftover data of the array is put within the header. So the arraylet data can be anywhere in the heap because the array is going to take care of it. And if you want to access, say, index 1, you're just going to follow that array pointer, go to that region, and access that, that element. So this is how arraylets are stored in the heap. And however, you can see there's some indirection there to access the elements of the array, and there are some APIs that actually require contiguous view of the array, and this is not the best way to do that. So that's the case of JNI, Java Native Interface Critical APIs, and JNI Critical is used when the programmer wants direct addressability of the object, meaning we can't just give the array, we can't just give to JNI the point to the header because it doesn't know how to deal with it, because it doesn't know what the data is, it doesn't know how to access the data from there. So what happens right now? So in order to pass this array to the J9 API, we actually have to copy element by element to a temporary array, right? That takes time, and pass that to the J9 API. J9 API does whatever it has to do with the array, and then at the end, you have to copy everything back to our arraylet leaves. As you can imagine, this is a very expensive operation. So that's where double mapping comes in. So we try to make large arrays, which are these discontiguous arraylets, look like contiguous arrays. If you're familiar with ZGC, ZGC also uses multi-mapping, but in ZGC they use multi-mapping to deal with multiple copies of the object of the heap, to have this consistent view of objects at the heap. And here we use to deal with this problem of having this contiguous representation of the array. So we leverage the fact that virtual memory in 64-bit systems has a very large address space, which we can heavily use virtual memory, and on the other side, physical memory is limited, which is one of the reasons that this optimization is not available in 32-bit systems. So what double mapping is doing, so we actually map two virtual memory addresses into the same physical memory address. And the nice thing here is that any modifications to the newly mapped address will reflect the original data and vice versa. So this is a virtual representation. So in the bottom again, we have our arraylet header. Here in the middle, we have the heap, and in zoomed in there, we have the arraylet leaves, and we map that in such a way in another contiguous virtual address space, so that the data associated with the arraylet leaves is going to be in a contiguous way. So for the JN9 API, all we have to do is pass the address of this contiguous region of memory, and JN9 can do whatever its operation on that contiguous memory region, and the modifications on this address is going to be reflected on the actual heap, because we actually double mapped those arraylets, which is pretty cool. And comparing operations from before and after using double mapping, array operations got up to 35 boost and speed up. And depending on your benchmark or workload, if you have many large arrays, this is a really significant difference. So this is a that was double mapping. And now I'm gonna go through some tables with some summaries on what I've talked to you about today. So here is a graph of a quick guide on the different characteristics of the different policies. So some of the policies are generational, like gen-con and balanced. Some are concurrent, have some concurrent phases. Up-throughput is 100% stop the road, no concurrent phase at all. Metronome, balance, and gen-con has concurrent phases. And different policies deal with the fragmentation of the heap differently. Gen-con has tenure, nursery, divide the heap into tenure nursery, balance in metronome region-based, and up-throughput has the small object area and the large object area. This is another graph that shows which domain is better for each policy. So gen-con is very good for web servers, desktop application, and runs most applications well. Balance is very good for large heaps, and if your system supports NUMA. Metronome is good for software real-time applications if you need an upper bound on the pauses. And up-throughput is very good for small heaps, or if you really want to maximize your throughput. Each, depending on the policy, we're going to have different addition of metadata that the GC needs to use in order to collect those objects. And different policies have different throughput and GC policies. So normally, the highest throughput you have, the longer the policy is going to be, which is the case of throughput. And you have some policies in the middle, like balance and gen-con, if you have a very good balance on the two. Here is a comparison between the policies between OpenGen9, Hotspot, Red Hat, Azure. So the ones at yellow, the ones that are at the top there are the common GCs, the ones at blue and green, they are pauseless GC. So gen-con is very similar to CMS from Hotspot. They're both generational. They have both new space and old space. Balance is very closely related to G1. Both are region-based, both are generational. In the blue spot there, we have the pauseless GCs. The lines there is not as thick as the ones above because they share a few similarities, but not everything. For instance, ZGC has multi-mapping, like I said before, which balance uses for the double mapping arraylets. It's also region-based, which is closely related to balanced and metronome. It does has a copy collector, and Shenandoah there has two versions now. The first version uses Brooks pointer, and the second version is more closely related to gen-con CS. Like we call read barrier, and Shenandoah I think it calls load reference barrier. So they do share a few similarities here and there, and at the bottom there we have Azure C4, which is a pauseless GC, which is requires special hardware, and sometimes you can get away with some special software as well. In summary, I came through a lot of content, but if there is something that I wanted to get off this talk with is that there's no perfect GC that fits all. So if you're looking for the highest throughput GC policy, you should go for a perfect stop the road GC. But if you do care for pauseless, then you should go for the perfect pauseless GC, because the perfect stop the road GC is not going to have like read and write barriers that you need to worry about. Therefore, that's not going to hurt your throughput. On the other hand, you have pauseless GCs, you need those write-read barriers to have a consistent view of the heap and the objects. Therefore, that's going to hurt a little bit throughput, but you're going to have shorter pauses there. We went through different policies and different ways to divide the heap, and that way we can defragment the heap in more optimal ways. Like I said, there's no perfect DC fits all. I do recommend you testing different policies for your different workloads and see which one works best for you. And within those policies, you can also tune them individually. So I also recommend that. And like I said, for the more puzzles you see you go to, you're gonna have these read and write barriers that you need to make sure you have this consistent view of the objects at the heap. So these are some links if you wanna go there and test out. Obj9 is open. We do encourage people to come test, contribute. It's an open project, it's very cool. Omar is another project. It's a project that has frameworks for you to build runtimes, and OpenGenI uses some of the tools at Omar, so I also recommend taking a look at that. And other OpenGDKs decide to go for the binaries. So that's all from my side. If you want to connect, it's my LinkedIn and my Twitter there. And like I promised, that's the book that I recommend if you want to learn more about GC. That's the Bible of the GC. There's everything you need to know about it. And very quickly, I'm already over my time here, and those are some very basic command line options that you should try. There's other ones that if you go to the OpenGenI site, there's other ones to try as well, but there's if you would start tuning your application, I would start with those. So that's all from my side. Thank you, and I'll take any questions.